Thank you. So I'm going to be kind of sort of shepherding and moderating this session, basically doing the exact same thing that Kate was doing before. The rules are the same. We're gonna have 4 talks, and yeah, try to keep it to 10 minutes for every individual talk, and then we'll follow it with a 20-minute kind of Q&A and pulse check of everybody who presented. So our first talk is called Pegasus at the Edge, and will be presented by Ryan Tanaka, George Papadimitriou, and Iwa Deelman. So I guess, Ryan, do you want to take it away?
Yeah, sure. Can you see my screen? Let me just put this to present mode. Okay, how's that?
Looks good.
Okay, great. Thanks a lot, Jason. So yeah, my name is Ryan Tanaka. I'm a research programmer here at the USC Information Sciences Institute. I work on Pegasus, which is a workflow management system that we've been developing over the years. So today I'm going to be talking about sort of our exploration into running Pegasus jobs at the edge. And also I did some work on benchmarking ffmpeg on Raspberry Pis and Jetson Nano. So that's something that Mike and Eric had mentioned in the previous section. Okay, so just to start, what is Pegasus? So it's a workflow management system. Scientists can use it to develop, run, monitor, and debug their workflows. We heavily utilize HT Condor as the underlying execution engine. And then one thing that I'll point out is that these jobs, when they can run in sort of shared file system or non-shared file system type of environment. So on like an HPC cluster or in the cloud, perhaps. So, just to quickly start, I'm going to talk about, Pegasus at the edge, what we did to kind of explore how we used Chi at edge. Then I'll talk about IoT hardware in your workload, which is where we benchmark ffmpeg. And then after, I'll sort of wrap things up. So yeah, starting with Pegasus at the edge, what we did was we first created HT Condor 9 ARM and x86 64 worker containers. I did have to compile the ARM version on my own. They don't provide that currently, but we have contacted them to see if they could sort of start providing that, as maybe people might want to start running Condor jobs on these edge devices as that becomes more prominent. We built a simple provisioning tool as part of Pegasus, which will sort of spin up workers based on how busy our job queues are and what resources we currently have available. And this is something that we plan to run in incorporating Chi at edge resources and also x86 64 machines like at the core or in the cloud. So what our provisioning tool does is it just looks at the number of idle jobs in the queue. It looks at the number of idle workers of the same architecture that what those jobs require. And we take the ratio of that, and that gives us some load threshold. And we just use that to, to spin up a worker if that threshold is exceeded. And then if we have any worker containers that are sitting idle for more than some max idle duration, then we tear them down just to free up resources, as some of these IoT devices, could be resource constrained in terms of hardware. These HT Condor workers, they are very well optimized and they do have a low overhead. But just as a best practice, we do try to free things up. And so that's what I'll show you guys in a second, how this provisioning works. So here I have 2 plots. So on the x-axis, we have time. So at time 0, this is when I start up this provisioner and also start submitting jobs into the queue. And then on the y-axis, we have the count. So starting with this plot on the top, the blue line represents the number of busy workers in the pool of all the workers that I have available. And then the orange/yellow line represents the number of running jobs. And in an ideal world, that yellow line will be right on top of the blue line, which is what we see. Well, we get kind of close. We can provision, almost just as good, but we can't predict some things. And so there's some space here, but that's okay. Another thing is that these workers, when you start them up, they are sort of busy getting ready and connecting back to a central manager before you can actually run jobs on them. And so that's why we also have this space here. Then on the bottom, I'm just showing the number of idle jobs queued, at a given time, and then the number of idle workers that we have queued. And so as we can see, as we get this sort of burst in demand in our queue, then we fire up some workers, they immediately start running the jobs that we need. And then this goes until the end. So this is just sort of our initial exploration into running Pegasus workflows on edge devices. And we're going to continue to use Kai at edge because it's great. I don't have to go and set up my own Raspberry Pis or Jetson Nanos. I can use the Python Kai interface to basically just spin up these containers as I need them. Like I don't have to go and set up these devices, put my SSH keys on them, and so on and so forth. So I really like that. Okay, so that was about Pegasus. And the next thing I want to talk about is sort of IoT hardware in your workloads. So this is talking about ffmpeg, how it performs on the Raspberry Pi and Jetson Nanos. So this is something that we did as part of the Flynet project. Mike and Eric mentioned that we're using drones and they're streaming videos, and so using these Raspberry Pis and Jetson Nanos, they're ideal candidates to do this. But we wanted to see to what extent can we use ffmpeg? How well can these devices handle running this piece of software? So what we did in our benchmark is this is sort of our test setup, where on the left I have a 2019 MacBook Pro that has 4 cores, 8 threads, 16 gigs of RAM, and a very fast SSD. So it's a good sort of control machine, which I know won't be a bottleneck. And then I have it connected over a network link that has a latency of about 4 milliseconds and a bandwidth about 112 megabytes per second to a Jetson Nano and a Raspberry Pi. And the one thing to note here is that these two devices are using pretty similar SD cards. And when I did some tests on those to see about how fast I can write to them, well, they get about 50 to 60 megabytes per second. So off the top of my head, I'm thinking, okay, if we're saving frames to this, that will be like the bottleneck. Obviously, one has a better GPU than the other. This Broadcom Video Core 6 thing is sort of like a low-powered GPU versus the Jetson Nano has this 128-core Maxwell GPU. And so this is what we did for the benchmark. So we have 5 identical videos. Each video is 3 minutes and 14 seconds long. It's recorded at 25 frames per second and encoded in H.264. And we have these 5 identical videos, or we have this one video at 5 different resolutions from 240 to 160 up to 1920 by 1080. And so if we look at the size of each MP4 file, this is the size of the video itself when it's nice and compressed. And then if you're to pull out individual frames from these videos, how large will these frames be? And we want to know this because if we're doing video analytics or any kind of sort of image recognition, we're going to have to process these frames. And so we're going to have to deal with this data. And so obviously the frame size increases as the resolution increases. But one thing to point out is that the total size of all frames, like if we were to extract all frames from these compressed videos, this is how much space it will take up. And so these are the scenarios that we tested. So with each of these 5 videos, we have the Raspberry Pi 4, which is running ffmpeg, streaming videos to the MacBook Pro as a client, and the client is always saving individual frames. Then we do the reverse, where the MacBook Pro is streaming using ffmpeg to a Raspberry Pi. And then we do the exact same thing for the Jetson Nano. And so we want to see, which one is better, which role is better suited for these IoT devices, and maybe what are the bottlenecks and how can we improve. So these are some of the results, and I'll just sort of quickly go over this. So on the x-axis here, we have frame number. So ffmpeg logs frame as it is streaming or receiving. It logs at a given frame number in the video, what is the current FPS? And so that's what we parsed out and took a look at. So when the MacBook Pro is a server and the Jetson Nano is a client, this is sort of what we see here. This dotted green line is native frames per second of the video. And so you want this yellow line that is the client to be receiving and saving frames at this exact green line, because that means you're sort of processing things in real time if it was being streamed real time. And as you increase the video resolution, performance degrades, and we guess it's probably because this SD card is slow. When we flip things around, the Nano is now a server streaming video to a MacBook Pro. It does pretty well up until 1920 by 1080. So now if I quickly jump to the same test, but using the Raspberry Pi, when the Raspberry Pi is a server streaming to MacBook Pro as a client, things work pretty well, again, up until we hit 1920 by 1080. However, when we go to the Raspberry Pi as a client, receiving frames from the MacBook Pro and saving them to disk, once we hit 480 by 360, performance gets kind of bad. The FPS at which we can save frames is kind of slow, and it gets pretty worse as we increase the resolution. However, we did try something else. So both of these devices have at least 4 gigs of memory. And what if we write these frames to main memory using like tempfs? And so that's what we did. That's what this purple line is. So as many frames as we can fit into main memory, we'll write them to main memory instead of to the SD card. And we'll see that the performance that we get here on this purple line is just about the same as MacBook Pro, which is great. So that's how we can sort of speed things up. And almost out of time, so I'll quickly go over just 2 more slides here. So we want to look at the duration that ffmpeg takes to run when it's receiving a video. And in our case, the video is 3 minutes and 14 seconds. And so we would hope that receiving and saving frames would take 3 minutes and 14 seconds, which at these resolutions for the Jetson Nano in blue, yes, that's what it takes. But for the Raspberry Pi in the cyan, it takes a bit longer. And so at 1920 by 1080, the Raspberry Pi takes about half an hour to like save all the frames of a 3 minute and 14 second video versus the Jetson Nano took about like 20 minutes. So some differences there. So just to quickly wrap things up, Chameleon Edge has been great because it's making it possible for us to test Pegasus on these different edge platforms and play around with sort of provisioning on these heterogeneous resource pools. One request that I do have is that it would be really great if, using Python Kai API to interact with Kai at Edge, if it was very sort of robust and reliable. That would be like, I guess, my biggest request, but great work so far. And then also, these 2 IoT devices, they do have hardware limitations, but as long as you're aware of what they are and what your workload is, you can get around them. And that's what we did by, looking at using main memory. So yeah, that concludes it. And thank you a lot for your time.
Thank you very much. And so I'm interested in come back to some of these questions during the panel, but for now, the next talk is called, it's a feasibility study for increasing pedestrian safety. And I'm not sure who is taking the driver's seat for this. Shirley, are you presenting?
Yes, I will. And then my students will also be doing part of the presentation.
Okay, great.
I'll just share my desktop so that when I follow a link, hopefully you'll be able to follow. All right, so so the title of our presentation is a feasibility study for increasing pedestrian safety. This is our edge computing team here at UTEP. So Airam is an undergraduate researcher working on this project, and Imran is a graduate research assistant in the PhD program in data science. All right, so the current status of our project is that we have spent about the last month on an IRB application because of the way we're going to be conducting this study. We'll be storing the videos. And so we do have to get the permission of the volunteers that we'll be using in order to collect the LiDAR and the video data of the pedestrian activities in the vicinity of vehicles. We're also learning to use the edge infrastructure, key at edge. And so we have created a project, Edge on the Border. And we've started trying to launch containers, finally been successful with that, but still having problems, as I think others have, another participant mentioned in the chat, with authentication or with running the container once it's created. But that's a debugging process we have to work out as new users. We have some experience with the software we want to run from having used the AI containers on TSC bridges to GPU nodes. So we have some of the tools ready to go for the machine learning applications we want to try on this data. We're currently pricing LiDAR devices. We may be able to borrow some from some other departments for our feasibility study. These devices range from low cost to very high cost. And we need to investigate what will be needed to produce the quality of data we need in order to do the near-miss analysis is what we're trying to do. So, and we're currently investigating the data analysis and the machine learning algorithms and techniques for doing this near-miss analysis. And also getting access to sample data sets before we've collected our own data. Airam will talk about the motivation for the project and the goals for the project.
Yes. Hi, everyone. So, unfortunately, it has been in the city of Paso, Texas, where we reside now, there has been an increase on the rates of pedestrian collision or pedestrian accidents. And what mainly motivated us was this neighborhood called Chihuahuita neighborhood, which is located on the central side of El Paso. And a fun fact about that neighborhood is that it's really close to one of the port of entries of the border from Mexico to, or Chihuahua, Mexico to El Paso, Texas. Therefore, we want to install some sensors, in this case, LiDAR sensors, to detect the trajectory from the pedestrians and to see what are the main causes of the accidents that has been in the neighborhood. So it is for sure, it's really important to determine the factors of contributing to this increase. Of course, to see the average, like what is causing these accidents. Identify high risk areas, therefore to let them know like, what is happening. And yeah, to develop strategies in order to save lives and of course avoid those collisions. Okay. So basically the goals of this study is to use LiDAR sensors, and those sensors will help us, like I said, determine the trajectories of the vehicles, bicycles, any transport source, and of course the pedestrians. We will also be installing video cameras to help us to get data and of course analyze it. And we will try to figure out which machine learning techniques or algorithms we can use to analyze that data in order to portray it. Thank you.
Okay, and Imran will talk about the LiDAR technology and also the near-miss analysis approaches.
Hi, everyone. So LiDAR is actually kind of like radar, but instead of radio wave, we are using light. So it stands for light detection and radio. So this kind of sensor, like what they do, they transmit a stream of laser light into one direction, or if they're a moving part, it can rotate 360 degree and make a 3D mapping of the environment. So that's a good thing with the LiDAR. Using this technology, we can actually distinguish between cars, trucks, pedestrians, and bicycles. So what we are intending to do, we are intending to use LiDAR sensors on roadsides or on the traffic intersections. So those kind of sensors will be actually stationary sensors, on contrary to the sensors that come with the smart cards. And we are trying to do is get those data using our edge architecture and trying to detect any near miss with the vehicle and the pedestrian so that we can come up with some kind of measures to prevent those kind of accidents. So by near miss analysis, we are actually what we actually mean that when a pedestrian or vehicle comes together in kind of situation where a vehicle had to abruptly brake or to swerve, avoid striking a pedestrian, or a pedestrian had to take sudden evasive action to avoid being struck. So for the near miss analysis, on a much larger data set, would be able to predict more reliably, like what are the causes of the crash and how can we like prevent those crashes. So for that purpose, what we need improvements on the we will be making some improvements with the data so that we can determine where to put additional crossings or where to put reduced limit speeds, speed bumps, or etc. So there has been a few work going on in University of Nevada, Reno, and on San Francisco. So we have put the list of those works here, and the common architecture is here. Like we have to first get the raw LiDAR data from the sensors, then on a machine like a server or in a laptop, standard laptop, we can do the rest of the work. Like first we have to do the background filtering, then we have to do the object clustering, then object classification, and later additionally we have to do like lane identification, object tracking, and find out like what are the trajectories of the object so that we can predict a collision.
Okay, thank you, Airam and Imran. So we have gotten access to some sample data sets. I won't take time since I'm probably running short of time. I forgot to note the time, so I think I have only a couple more minutes though. But there are some pedestrian LiDAR sets, data sets available from Arizona State University. Velodyne also has some, as well as a visualizer. And then the Velodyne also has a GitHub with Python code which can process these data sets and allow you to produce training and test sets that you can use with various machine learning algorithms with a Python API or interface. And then also Chattanooga Martin Luther King Smart Corridor. So that is a project led by at UT Chattanooga by Minas RTP. And they have gotten a new NSF grant, and part of their new grant is expanding that coverage of sensors and using LiDAR sensors in addition to their video cameras. And they have done work on a near-miss analysis for vehicle collisions. And they're also providing shared access to researchers who would want to use some of their data in order for their research. So how do we want to use the key at edge testbed? So ideally, we would like to be able to connect our sensors to the infrastructure. Otherwise, we can transfer the data in another way. And then we want to investigate how to orchestrate the data and computation from the edge to the cloud. This is similar to what Chattanooga has investigated there. And interestingly, it's not just the performance optimization, there's also privacy constraints, and the constraint they have on their video. Part of the difficulty we've had in getting approval for this project is that video, if people have access to it, they can do facial recognition. And so that is a privacy concern. So the way they process the video data at the Chattanooga project is to, as soon as the vehicle has left the field of vision, they process those frames immediately and then throw the frames away. They do not keep them. They do that on an edge device. They need a fairly powerful edge device with GPUs in order to process the amount of video data they're collecting in that corridor. We also want to evaluate different options for the edge servers, similar to the situation in Chattanooga, with respect to the communication needs, and then the computation needs and the communication that we have available. We have a little different situation. We don't have the high bandwidth fiber optic network that they have in Chattanooga. So our situation will be a little different. And then also evaluate strategies for the data transfer and storage and access. This is with respect to performance, also on being able to reproduce the experiments. And then there's privacy and confidentiality concerns as to what data can be kept. There's restrictions with the IRB as to how long you can keep. You cannot keep data that has identifying such as video data indefinitely. And then things like that have to be worked out with the city and the Department of Transportation if you're actually going to implement this kind of thing in the city. Ideally, we would like to, as Chattanooga is doing, be able to share our data, or at least the analysis results if not the raw data itself. Raw LiDAR data shouldn't really be a problem since it does not identify the individuals, but just whether there's a pedestrian or a bicyclist is something you should be able to figure out from analyzing that data, but not the identity of people. So to the extent possible, we'd like to share the data with other researchers. And just an acknowledgement, this research is funded by my UTEP startup funds for myself as new faculty at UTEP. Okay, so thank you.
Thank you.
Thank you very much. I was just actually in New Mexico recently, and I understand this problem is going to be a priority for them as well at the moment. It's like exactly this thing. So it was interesting to learn more about it. The next talk, we're running just slightly behind, but not too bad. Next talk is understanding reliability on shared edge. And I believe that will be presented by Junchen. I hope I pronounced that right. And if you want to decloak.
Hey, you guys can hear me?
Yes.
Okay, so let me try to share the screen first. Okay, you can see the screen, right?
Mm-hmm.
Okay, so yeah, thanks. I'm Junchen. I'm a junior faculty at U Chicago CS. Here I will briefly introduce the project Haryadi, another faculty in our department, and I and a few of our students have been just started working on this summer, which is really enabled by the Shared Edge platform. So Haryadi and I have worked on other edge-related projects, but this one has only started very recently. So there's only preliminary results, but hopefully our early experience can highlight the benefit of Shared Edge and our feedback that might be useful to the community. So the main motivation of the project is that is the observation that AI-powered edge applications are growing fast. In particular, video-based AI applications like augmented reality and traffic video analytics have been increasingly used as enabling tools for in businesses and in public safety, as other talks has mentioned. Generally speaking, in edge computing market, software is growing faster than hardware, which suggests that more software applications will likely share the edge devices. And moreover, these edge applications typically require very high accuracy as well as low latency. So in this context, it's very vital that these shared edge services provide reliable performance when multiple edge applications compete for edge resources in terms of computing and narrow connections, narrow bandwidth. Then our goal, therefore, is to address the key system challenges in a shared edge environment that enables real-time application, accuracy-driven applications. And to be more focused, we choose a few video analytics pipelines as a case study. An example video analytics pipeline can be something that collects video streams at edge device and then use edge local compute power to quickly detect objects in it. And many pipelines also send video frames back to cloud servers to collaboratively achieve more accurate analysis. A range of video analytics pipelines have been proposed these years, in recent years, and a common theme behind them has been that in their designs, there must be a need for highly accurate analysis and low latency, and both of which require running more compute on edge devices and minimizing narrow traffic to the cloud. It seems to be, I mean, these designs seem to mitigate the resource pressure on the edge device, right? So after all, you're minimizing the resource demand, but there's a catch. The catch here is they basically create more and more bursty resource demands. Okay, here we show a video analytics pipeline called Glimpse, and what it does is that it tracks existing objects in simple algorithms to track existing objects in the video stream and then send a frame to the server only when new objects are likely emerged and you need powerful analytics by the cloud server to detect objects, but otherwise it will be just running simple algorithms on the client. So this seems pretty reasonable, right? So in terms of reducing the load of the edge device, but consequently, if you look at the graph, right, so they lead to very highly variable resource usage in both compute on the left and bandwidth on the right. And we try to demonstrate it on edge, real edge devices with the Chia Edge devices platform. And we built a test bed using Raspberry Pi and Jetson Nano devices, which are also connected, conveniently connected with bare metal Chameleon servers acting as cloud servers. So we built this pipeline, one thing to note is that the current Chia Edge platform only allows us to run programs within a container environment. So we created, so what we did was we created and loaded a single Docker container that supposedly has access to all resources on that Raspberry Pi device and run multiple instances of a video analytics pipeline, in this case called DDS, which is a paper we published last year in SIGCOMM. Here, what DDS does is it uses the server-side feedback to iteratively decide how the videos should be encoded at low quality while still preserving enough information for the DNN on the server side to detect all objects. So it's a pretty typical video analytics pipeline these days. And of course, our measurement shows that there are bursty resource demand. This is basically what will happen if multiple DDS instances are running together without appropriate resource sharing. Here you can see that the CPU demand is already quite variable for each DDS instance. But actually, if you run multiple of them together, it will have more bursty and unpredictable behavior. Same thing with bandwidth usage. It become more bursty and more unpredictable when multiple DDS instances run together. So such temporal variability of resource usage, of course, makes resource sharing on the edge devices across multiple pipelines very, very challenging. Basically, if the resource demand isn't met in time, it might lead to low accuracy. Basically, some small objects might be missing, or high latency, because all objects in a frame cannot be detected until the inference on the whole frame is finished. So as a result, the inference result might be rendered useless if the resource demand isn't met on time. And today's resource sharing strawman are not ideal. Without any isolation, there can be high tail latency when multiple bursts occurs at the same time. And if equal resource is allocated to each pipeline, well, there can be resource wastages because these video analytics pipelines aren't using resource actively all the time. On the other hand, however, these applications, these video analytics pipelines are not rigid. Basically, they can easily trade accuracy for latency depending on the availability of resource, although they don't know the resource availability these days. So this suggests some new opportunities. And our overarching goal in this project is to try different resource allocation schemes and ultimately propose new ones if needed in order to maximize min accuracy and minimize max delay. Okay. Now, our technical approach includes two components. Again, this is early stage, so I'm just talking about potential steps here. We will explore ways to continuously profile impact of the bandwidth and latency on analytical quality of edge applications. Now, here quality can mean accuracy as well as the result freshness. And this can be challenging to monitor because these are AI pipelines. You have to run inference in order to know how much low accuracy or how much delay you will experience. But our recent work has kind of indicated that it's probably doable by leveraging existing outputs of the DNN engines. I'm not going to go into details here because this is still future steps. We will also explore different types of resource sharing mechanisms, including traffic shaping and cross-layer solutions. But again, this is early stage, so not much results to report yet. So before I stop, I want to quickly say a few words about our experience with Chia Edge so far. Now, when our project started a few weeks ago, we were probably one of the few projects that run video analytics pipelines on Chameleon edge devices, including Raspberry Pi and Jetson Nano. Our experience so far has been quite positive, of course. We use Raspberry Pi for video pipelines that don't require much CPU RAM cycles. And we also use Jetson Nano as part of the prototype of one of our recent papers, where a simple VGG16-based DNN needs to run at 30 frames per second on an edge device. And once we manage to run that on the Jetson Nano device from Chi at edge, it runs pretty fast. It exceeds our expectation actually. And a added benefit that we found pretty handy with Chi at edge is that these devices, these edge devices, can be easily connected with the bare metal Chameleon servers, acting as sort of a cloud servers. And so you can build end-to-end pipelines quite easily. Now, there have been issues, of course, when the students try to set things up for the first time, such as creation and loading of specific Docker images that they created by themselves. And sometimes there are incompatible TensorFlow versions on these devices with the containers. And also sometimes the cache files kind of overload the disks. And but fortunately, the Chameleon team has been super helpful, very responsive, and most of the issues have been addressed in a day or so. And as always, there will be more issues emerging as we go along. For instance, we found that for resource allocation projects like ours, it's important to have direct visibility and direct control over CPU, GPU, and network resources. Unfortunately, basic tools like Linux TC, which controls bandwidth usage, or NVIDIA SMI, which monitors GPU usage, pretty popular tools these days, are not easily run within the container sandbox. And we wish to work with the Chameleon team to address these issues in the future. Now, but again, all these use cases and positive experiences give us confidence that these issues can be addressed and the platform can benefit a wide range of similar projects. Okay, I'm gonna stop here. Thanks.
Thank you very much. It's really interesting to sort of see this noisy neighbor problem and how it gets extended to the edge. So, and I'm sure there's some things I'd be curious to ask you at the panel, but we should move on to the last talk of this session and the last talk of the workshop. Last but not least, applications and network measurements for SDR on Chi at Edge. And I believe that Taimoor and Joshua from Iowa State will be presenting with some backup from Mike at UChicago potentially. So take it away.
Yep. Thank you, Jason. Yeah, and we are going to talk about the SDR, the software-defined radios, and how we have been using them with the Chi at Edge testbed. And we are going to also demonstrate a demo with reference to the applications that we enable at Airam that Dr. Jiang talked about in the first session. And we also are going to talk about how or why Chi at Edge is the most suitable platform that would support the applications that software-defined radios enables. So some, not all, but some of the example applications. So we can see here that the agricultural robot with sensors. So here is a robot in a field, and it is doing some real-time, high-throughput phenotyping with high-resolution imaging sensors. One example project is PhenoNet here at Iowa State University. But this is where we are going towards the smart agriculture or the digital agriculture actually that Deep maybe mentioned earlier in the first keynote session. Similarly, other applications like in transportation, for example, we have a golf cart here, and it is communicating with the control tower or with the base station and over the wireless link to send that control information for real-time control actually. And that's where the Chi at Edge brings the capabilities here to process that data on the edge to mimic the real-time environment actually. And similarly on the precision livestock farming and rural education, that is connecting the classrooms to the fields and bringing this rural STEM education realize it with the AR and VR applications. And similarly, the imaging sensors, the different imaging sensors that are working in the agriculture or on the other applications specifically So from the SDR's perspective, so Jason was talking about the camera on his apartment window. So that camera is going to go mobile with the SDRs, because we are going to have the UE devices, the client devices on these robots, and the cameras or the sensors would be attached to those SDRs actually, and it would communicate with the base station and send the control data or the sensors data or anything like that to the base station and process that on the edge or on the cloud. Now, not just the applications that we talked about, but the cutting edge or the state-of-the-art research on the wireless network as well. For example, the channel sounding, massive MIMO, millimeter wave. So a lot of system studies that are going and researchers are working on them. So we are kind of providing a platform for, like from the rural broadband perspective to have those kind of studies on the wireless channels or on the specific like applications. So here we can see like this diagram. So we have a base station here, and like this is from the perspective of how G@Edge works for the Era architecture that we have here, is that we have these base stations. So we have these 3 SDRs attached to this base station, and there are the client's devices that we call the UE, the user equipment. So SDRs are attached to those devices as well. And the good thing is that we can support parallel experiments, or like I would call this like infrastructure or resource virtualization. Like, for example, this would be a separate slice, actually, like the users would launch container on the base station, and one on the base station and one on the client, establish a connection between the SDRs. This is the wireless connection, and do experiment. And parallel experiments would be possible like in near future that we envision right now. And one such slice have been used in the demo as well. So here is the demo network. We have this base station in our lab. Like this is the base station SDR, and this one is on the right side. We have this UE SDR, and they are connected to the Iowa State network and over the public network to the G@Edge side. And we are launching containers on these base station and UE devices and running the protocol stack and the demo actually that Joshua is going to talk about. Yeah. Joshua?
Yeah. All right. So Taimoor, can we move on to the next?
Yeah, sure.
Yeah. All right. So so there's a live demo of the software-defined radio experiments performed in the Era sandbox here in the ISU, leveraging the G@Edge. So we have the SRS-RAN protocol stack, and we are running these on the base station and then the UE to establish a seamless link between the UE and then the base station as well. So like on the top left, we have the a healthy real-time console traces from the SRS node B for 100 physical resource blocks network configuration, showing the downlink and then the uplink channel parameters such as the reference signal receive power, the bit rate, SNR, and then maybe block error rate and all that. So on the bottom left, you have the same for the UE, showing important metrics as well. So one interesting thing about G@Edge is the Jupyter notebook that we actually leverage, which is on the right-hand side. So instead of using the CLI to establish a link between the base station and the UESDRs running the containers, you can actually write a Python script in this Jupyter notebook, and which is of course, really interesting feature of G@Edge to structure your experiment on the G@Edge testbed and even record signal channel metrics like bitrate and all that. So basically, this is the sandbox experiment that we've actually leveraged G@Edge here in Iowa State University. Yeah.
Okay, so had our students this summer, Isaac, do some experiments over what we had available in G@Edge at the time, and they're similar to the experiments that we plan to do over the SDRs. One of the big differences is because we're testing between, say, a container at the edge and then servers at G@UC or G@TAC, some of this traffic is running over the public internet. And so we're measuring kind of these channel and link properties because we don't know what assumptions to make about that public connection. And ours later work is going to actually have control over the full path for repeatability. And so these were just some of the different examples and cases that were tested. So the top row here was a streaming application with, this was measuring the time between frame arrivals. So this is both latency and jitter displayed there. And then the bottom one is what bandwidth and packet loss each of these links could support. And so the goal was to see which of these network properties were important for the different categories of application that Taimoor mentioned earlier on with streaming or real-time control, and which links would support that, and choosing between a server that's close by, server that's far away, and just kind of leveraging the current state of Chi at Edge to start exploring that and see what tools are needed for researchers. So Taimoor, did you want to go on about how some of these were kind of useful
sure.
for?
Yep. Like why Chi at Edge, an important question like for ERA. So the first thing is about the infrastructure virtualization. So with containers, what we can do is that the diagram that I showed earlier, we can actually run parallel experiments. So that would actually maximize the use of the testbed between different experimenters, and parallel computing resource usage would be possible. And the other thing is about the latency. So there are some applications which are actually real time. Like by real time, like if we talk about that autonomous vehicles. So what we can do is that we would have this leverage to process the data on the edge, like on the base station side. Or if there is an application that is near real time or like not real time, so maybe that data can be processed in the cloud as well. So we have these different kind of links or different type of computing resources available. Like on the edge, like on the ENB side, we have these host computers, like host computing machines where we can run some computations. And then like on the near edge or the far edge. So we have these different capabilities that ERA architecture actually supports, and the Chi at Edge as a baseline. And similarly, another thing is about the parameterizing the experiment. So on the wireless resources, we have these frequencies and resource blocks and transmit power and like things like these. So actually it would ease the like the researcher to or the user to run an experiment, for example, from the pre-made images or like pre-built images to like allow the experimenter to start quickly. And then if there are any changes that that they need to make, that they can be made like during the experiment as well. Yeah. So this is how Chi at Edge support our ERA architecture, and this was all from our side. Thank you.
Great, thank you very much. And a very cool little demo as well. So at this point, I think we're running a bit late, but I still think it would be worthwhile to take some time to do the panel discussion and allocate the full 20 minutes. So I'd like to ask that Taimoor, if you want to stop sharing your screen, and then if all of the panelists can decloak, so we can do this kind of Q&A thing similar to how we did before. And just to sort of kick things off, I do think that the first question that that Kate actually asked in her session is just kind of a good introduction question, asking, you sort of went over this in the talks, but I think it's good to reiterate, like which aspects of an edge to cloud platform such as Chi at Edge are most useful to you. You know, whether it's making your own devices shareable, the Jupyter interface was mentioned, or if the sort of access via federated login, or the ability to access both edge and cloud. So do we have the, yeah. So I guess people already answered this poll once already, but just what's up there so we see the options. So maybe Taimoor, because I see you're highlighted in my interface, if you want to chime in.
Yeah, so as Joshua mentioned as well, like the Jupyter notebook. So at ERA, actually, we would have these experiments, like the customized experiments, for example, for specific frequency blocks or resource blocks that we want to dedicate to particular experiments, experimenters. So those kind of templates can be made like for orchestration purposes as well. So like user would just launch like a pre-built template like from the Jupyter notebook, and that their experiment will like start. And that's pretty cool actually about it.
Yeah, to us, I think the most important thing is, I mean, the most useful thing, of course, is the ability to build this end-to-end pipeline across edge and cloud. And then that's been very handy for us, because otherwise the student has to buy the device and then connect that device with our servers. I mean, maybe some lab servers with a stable network. This is definitely not always the case. Sometimes you have to go through public internet, and it's not always doable. And because you have this wide pipeline, right? So you can then do bandwidth throttling. At least in theory, you can do bandwidth throttling to emulate all kinds of network connections between the edge and cloud. So that's that to me is a very useful setting.
Thank you. I see Shirley has her hand raised virtually.
Yeah, so basically ditto, that accessing both the edge and the cloud, and then being able to experiment with the orchestration of the data and the computation between the edge and the cloud, and also the different edge devices, because in our feasibility study, we were wanting to evaluate this, and not having to do it by trial and error is really an advantage, and to be able to present that, you know, when we do go to the Department of Transportation and present the results. So this is very useful. And also some of the results that have been presented today in the performance modeling, the performance results, I think will be useful to us in just planning how we things we decide to try.
Shirley, if I can pick up on the last comment that you made, how should those results be shared to be most impactful to people like you?
So if we can make use of some of these performance models and some of the tools that have been developed, I think that would be very helpful. If there's, you know, a way to share those with the Python notebooks, possibly, so that we can run our own experiments, you know, with the tools that have been developed.
So if you were, well, we have the Trovi infrastructure. If you were to find a Trovi bucket with the Jupyter notebook that has some tools or performance valuations and things like that, with the notebook and the image and things like that, would that be suitable?
You know, we might have to adapt it to our case study or our application.
Sure, of course. I mean, so you would then copy it, and but you'd have an example. You'd have something to work on. Okay, yeah.
To chime in on that, from the earlier talk with the autonomous cars, the way we were planning to share that was having both the notebooks that let you collect data and train it, as well as the trained models from that data set and the tools to kind of plot the output results. And so you have a kind of a baseline result ready to go to compare against.
Yeah, that would be very helpful.
Thanks. I wanted to move on from that sort of warm-up question, which was already had a lot of interesting responses, to talking a bit more about, it seems like one thing that was coming up in a few of the talks was sort of having a little bit of a limited access into the features that you needed of the edge device because of the container. And it sounded like there is a bit of a, you know, desire to be approaching more of the bare metal. So one question, so I guess as an introduction to the question, I wanted to say that though the edge platform is currently exclusively focused on container orchestration and launching containers, I don't really want to signal that that's something that we're like, you know, ideologically committed to. I think that bare metal, there's probably, it will be sort of two flavors of doing edge development depending on what the needs are. And, you know, bare metal is significantly more difficult to do and scale, but there are some obvious upsides to it. So I guess the question is, like, what features of bare metal level access are you using for your current, or would you plan to be using for upcoming experiments? So like, what kinds of more fancy features do you kind of require? And I guess there we have in the poll, we have access to devices on the host system, sort of like some sort of perf monitoring integration, and access to system resources, different container capabilities, and then other is kind of grab bag of things that we did not think of.
Yeah,
Thanks,
I know.
Taimoor.
I know as we've kind of gone along on some of these projects, we've found it's sometimes hard to know beforehand what bare metal features you're actually using. It can be kind of a low-level assumption, and then you move to a more constrained environment and things mysteriously stop working. And now you're in there and you go in and find you really actually relied on certain system calls or access to certain kind of privileged devices. And so I think it's going to be really interesting to find out what everything depends on as we start seeing more people's workloads.
I think in yeah. Sorry, I just quickly
Right,
wanted to
go
add
ahead,
that. So, okay. Yeah, one thing that I did try is initially I wanted to be able to start up containers in privileged mode because some of the work that we do involves having containers running containers, and to get that working, I need privileged mode. But again, if you can't offer that, I do understand if it does add some complexity. But it is one thing that I did try, and it would have been nice to have at the time.
Yeah, so ditto on both points. It's hard to know what's needed in advance, especially if the students. I mean, when students are working on it, they probably want to. I mean, they search around and find, oh, here's a solution. But when they try to use that solution on convenient devices, their access issues and privilege issues. So it's a dynamic process, and I understand it's hard to do that upfront. So that's why when Haryadi and I work with the students, we always ask them, do you need direct monitoring capability or control capability? Because if it's monitoring, there could be a workaround. If it's control, probably you need a real direct access. And sometimes the control capability can be kind of equivalently emulated on the server side. Because I mean, for example, in our experiments, sometimes you need to throttle bandwidth, and you can do that on the server side as well, right? Kind of equivalently, because it's a two-way connection. The other point I want to make is I totally understand there are benefits to provide this container abstraction. As a matter of fact, when I talk to industry collaborators, they always, I mean, their business models usually when they provide these so-called edge services, they're figuring out how to do that. But the service model they provide is containers. They want users to upload their programs, and they run these programs within their container process. But as as system researchers, right? So then our research probably would be trying to provide services for these containers. So sometimes there's different levels of depending on where you're looking at, right? So if it's business world, you probably would be developing within containers. But if you're trying to build better system for that, you need to go deeper.
Thank you. It's really, really valuable feedback. And I also I'd be interested to touch base more with some of you all to understand more like the specific needs. Like I know, like Junchen, you kind of made it sound like there was like you needed like net admin or some other capabilities, and some of the stuff I think we can explore, but we're always kind of evaluating what's the security impact of this. Like going to privileged is kind of a no-go as far as we're concerned, but like, what else could we do? Like I know,
right. Like I said, it's not like we're not saying it has to be done. Otherwise, all experiments will halt. It's a dynamic process, and like I said, the students probably will be being aggressive if they want to have all access, but not all access. I mean, sometimes you can do things. I mean, there are workarounds. You don't need direct access to the lower level systems.
And I think also, I mean, we talked about restricted devices before, and there is a case to be made that if you're in control of the device, you can take the level of risk on that you wish, as long as the entire system health is not compromised. So that's something that I think also it'd be interesting to explore. If you had your own devices and you just wanted to manage them with Chiat Edge, but we're okay with privileged containers, like is there space for that? So it's interesting. I wanted to move onto a similar flavor of a question about sort of needs, but on the networking side of things now, because there's a lot of networking experiments happening here in this group. And so the question is like, just general, like, what are your needs from the network? Are you more concerned with capping latency to the cloud, having like low latency connections, or having bandwidth allocations? Do you want sort of faster connect or local connection between devices, being able to connect devices to other entities on the device's local network? So for instance, if you had some devices deployed in a shared lab and you wanted access to some other thing in there, and some other type of, I don't know, quality of service guaranteed stuff. So that's the question now to everybody. Again, everybody who's even not a panelist, feel free to answer. All this is really valuable. Doesn't seem like there's a clear winner in this one. It seems like everybody has a lot of different things that they need, which is interesting. But yeah, I put it to the panelists.
Yeah, so like maximum bandwidth and maximum latencies are like always kind of like they are required for certain applications that we talked about. Like most of the applications that the presentations covered today, like they were like mostly they were similar, like talking about real time or things like those. So for those kind of applications, actually the latency or the bandwidth is kind of critical. Yeah.
I had a question specifically to Shirley, because it sounds like you're going to be deploying lots of stuff in very remote environments eventually, but it wasn't clear to me if you were going to be using Chia Edge mostly for like internal testing or actually using it in those remote environments.
Yeah, so it could end up being both. So for the feasibility study, it will be for testing and for testing configurations. And I think the things that I mentioned about being able to throttle the network and kind of emulate different network bandwidth is going to be very useful to us. Then in the long term, we will definitely need a cloud infrastructure. We did put in our IRB application that we're going to be using Chameleon and Chia at Edge, and that with the security and that you have in place, authentication, that kind of thing. So, but we'll have to make a choice. I know with Chattanooga, they make heavy use of Amazon web services because they do some of the machine learning applications in the cloud. And then they do some of the analysis on the edge devices. So they have a use for both, and especially if they want to aggregate data from different sources, they're going to do that in the cloud and do the analysis in the cloud, do the machine learning training in the cloud. And so I think for the feasibility project, it's really for studying the strategies. For the actual production project, we will need some cloud infrastructure, and what we use at that point, I guess, will depend on a lot of factors. And satisfying requirements for security and confidentiality and all those kind of things. So,
yeah, of course, thanks.
Mm-hmm. On networking, one thing I thought was kind of interesting is all the talks today really assume that you have a continuous connection to the internet and to the cloud, that it's always there. And if your device is mobile, that's maybe not always the case. I'm just curious about people's thoughts on that, or if that was important to your work.
Yeah, absolutely. I mean, so with the FlyNet project, and I think what you heard from Mike and Eric, where we have these drones and they're flying past these towers, like the connection, is going to vary over time. And if we want to simulate that, then that would be, very useful for sure.
Cool. We've got just a little bit more time. I've got 2 more questions I'd like to get through. One of them is pretty, just kind of a small question, just getting a check on what kinds of deployment styles people are doing. Kind of interested in, are people going broad? Do people want to go use just single devices? So I guess thinking about your experiments, are you kind of more interested in sort of loading a bunch of like containers onto a single device, having them talk to each other that way maybe, or support each other? Are you interested in spreading out across devices, but within one site, kind of emulating like almost like an edge tower type thing, or a remote site? Or are you interested actually in combining resources across a wide geographical area and then networking them in some fashion, or some other one? I'd be curious what the other one is in this situation. So yes, whoever would like to start.
So I probably gonna I prefer someone go with the conventional and the first three conventional answers first, but my answers was kind of like the fourth category, because we're basically running multiple applications within one container. We're trying to have one container that has supposedly access to all resources on one device, because we're trying to do resource allocation. And if you have multiple containers running on that device, the allocation is basically done by the underlying system. So that's why we have this workaround. Yeah, I'm curious what my use case probably is atypical, I would say.
I was going to say you found the one thing we didn't think of, which was a single container, single device. Cool.
I'm not sure, but I think for our application, we're going to have a pipeline. We may want to have a different container for each part of the pipeline. I'm not sure if that's the best way to orchestrate it, but it might be useful to have multiple containers on a device in order to do that.
Something else that I think we forgot to ask on here is, how persistent are these containers? Is it like launching things repeatedly and requesting lots of devices repeatedly, or is it kind of longer running services?
So in our case with Pegasus and trying to provision these resources, it would be constantly starting things up, shutting them down, starting them up, shutting them down. In the case of like just benchmarking stuff like I did with ffmpeg, it's kind of ad hoc. I just need to start something up, have it run for a bit, and then shut it down. But definitely, with Pegasus and the provisioning, it would be like nice to be able to consistently and reliably spin up containers, shut them down on whatever reservation that I have. So I guess it's a mix of both.
Okay. Thank you. I think we're kind of at the tail end of the panel. So I wanted to end with the same question actually that Kate ended with, question of just sort of priorities, like how can we as the platform best serve your future experiment needs? Like where should we ideally invest the time? And so again, the options are like, do we invest on building out and scaling out the hardware? Restoring the availability SDK means allowing you to enroll your own devices and manage them on the platform. Or is it more of like sort of tightening the bolts, improving robustness, or scalability, or in being able to deploy the entire thing yourself with G8 Edge in the box, or something else?
Yeah, I like the fact you make this single choice question, because I was trying to click module of them.
Then that's another priority.
So I see that restoring the availability of the SDK seems pretty important, and that kind of, I can understand that, because it seems like a lot of people are interested. You have devices and you are interested in basically using the platform to manage them.
Yeah, I see that the G8 Edge in a box also has a vote though, and I think I was wondering realistically how many people would need that, but it looks like at least some people think it's useful, so that's important. I think the SDK though is a more practical option probably for more applications.
Yeah, and I did hear a few times, like it's nice to hear that everybody was able to work through the issues they have in our little nascent edge platform, but it does sound like the basically improving reliability of just making things start up more reliably and more predictably is very important. So we take that seriously, but it's good that doesn't seem like it's gotten in anybody's way too much. It's more about streamlining the user experience.
It's kind of hard to debug when things go wrong, but that's kind of always the case when you've got these layers and containers, and I guess I'm used to, the supercomputer environment where I can pretty much debug anything if I have to, but it's hard to figure out what's going on in this environment and what's going wrong and how things are being done. When you get an authentication error, how is the authentication even being done? Can't figure it out,
Yeah, I kind of agree with Shirley. So like sometimes what I would do is I would use the GUI to spin up containers. And then, if I run into an error, the error message is typically something along the lines of you have an error. And so then I'll just switch to the API because then I know I'll get the HTTP code and, like a nice verbose error message. And at least I can know exactly, what's wrong. And then, if I reach out to you guys on the Google group, then I can provide a more, specific error message as to what went wrong as opposed to a screenshot. So yeah, that would be nice.
Yeah, that's what I wanted to do was use OpenStack, but I'm getting an error on that. So I need to post a message to the users about that because the only thing I can get to work is help and exit. Everything else gives me an error. So, but yeah, I would go that way. I'm a command line person. Yeah.
So this is actually, those are good conversations to hear. And I think that the most valuable aspect of the user meetings, chameleon user meetings, when we were running them, is actually users talking to each other about various different strategies of how to run things on the test bed and ideas on how to factor your experiments and things like that. And it's sad that we haven't been able to do that for a while. So it's good that we at least have a virtual meeting. And this is perhaps as good a time as any. We're getting to the end of the meeting. And I don't know, Jason, if you had more questions in the panel or if you wanted to wrap up.
No, I think that it's time to wrap up. And yeah, I want to thank everybody for like all the great talks and all of the insight and perspective.
Yeah, I have to say just a few final words. First of all, thank you everybody for trying the infrastructure. We understand that it's not perfect, and we understand that it takes a little bit of perseverance and finagling to get to run. So we really appreciate your effort. And then also thank you for coming here and presenting and sharing your experiences with us. It's really, really important to us. I have to say that listening to all the applications and of course, monitoring the traffic on the mailing list and talking to many of you in person gave me the opportunity to be involved ahead of time. But Shirley, for example, I did not know about your application until relatively recently, till you guys submitted the abstract. So it was fantastic to meet all of you. I was really surprised by the breadth of the applications and by how fresh and different they are. I think that people are doing things that just simply were not done before. I think this is the great new frontier. I think in a few years, if we have a workshop like this, we're going to be talking about completely new things that we haven't thought about yet. So very impressed by the freshness of the applications, but also by their potential to change the world, right? So we've got anything from precision agriculture to Shirley's safety application with great societal benefits. I think it's amazing the potential that we have here working on the test bed. I think that one thing that we didn't ask explicit questions about, but that came up particularly in this panel, is how important enabling sharing between various different experiments going on is, how somebody might get started because somebody else did fantastic performance evaluation of various different architectures. And I think that what we would like to do is make sure that the sharing takes place. So if you have ideas for what you would like to find and how you would like to find it and how you'd like to share your own work and what prevents you from sharing, and it could be lack of incentive that prevents you from sharing, please talk to us and tell us how we can make that better. We'd really like to work on that. And then last but not least, I'd like to give a big shout out to the whole Chi@Edge team. You guys are wonderful. You built a test bed in record time, also an impossible time. And it works, and it clearly is very useful to others. So thanks very much. Maybe all the Chameleon team members, could you please decloak yourself and come and wave and make sure that everybody remembers your face. You're going to be working together some more on the mailing list. So thank you to everybody for coming. Thank you for your comments. You know where to find us. Please send us mail if there is something that we didn't manage to capture today. Thanks again.
All right.
Thanks, everybody.
Thank you.
Thank you.
Bye.
Thanks a lot, guys. Bye.